Hey class, we got something real important to show you. So just sit down and listen. You know we've been together such a short time. And now we've got to lay this on the line.
Wow, you know the semester's over and our schedule's open wide. I gotta show you something so you know what's going on inside.
A problem so important, so don't let those pencils drop.
And read this slide, it's a particle in a box. Ain't gonna show you something classically, we're just gonna explain it theoretically. Not gonna show you an oscillator, we're not gonna use those ladder operators. Not gonna show you electron spin, you'll need a professor to fill you in.
But we can show you the results of,
if you know what I'm talking about.
A particle in a box. A particle in a box, yeah. Particle in a box.
ooh, particle in a box, babe.
See, we're wise enough to know what limits are given. Yeah, there's more than one. And now we're gonna show you how to get this done.
To all those students and professors to impress, it's easy to do, just follow these steps. 1.
From what we know of an infinite potential well, or particle in a box, we know that outside the potential well, our potential is infinity, but inside, it's going to be equal to 0. We can use this in our Schrodinger equation to find that negative h bar squared over 2m, second derivative of psi is equal to our negative e of psi. We can then move this around to get this expression here. By letting k squared be equal to all of our constants here, we can rewrite this second order differential as this wave function here. This is our general solution, but what we need to do is we need to find a more specific solution, and in order to do that, we're going to apply our boundary conditions. For our first boundary condition, we know that x equals 0, psi equals 0, because it's going to be a continuity relation between outside and inside the potential well. We can apply our x equals 0 to our wave function and find that this is going to equal 0, but our b cosine 0 is going to equal 1, or is going to equal just b. So we find that b is equal to 0. We use our other boundary condition where at x equals L, psi equals 0 to find this expression. But we can't let a equal 0, so we have to modify k in order for our expression to always equal 0. And what we find is that k must be equal to n pi over L. Now we have this solution for our wave function, but what we have now is this normalizing constant a. So what we're going to do is we're going to apply quantum dynamics to find that to find our normalizing constant. And what we know is that if we integrate from 0 to L of our wave function multiplied by its complex conjugate and set that equal to 1, that we'll be able to find our normalizing constant. And what we get here is this expression for our wave function squared. And we can apply this trigonometric identity to simplify it a little bit more. And what we'll end up getting is that this cosine term just goes to 0 when we integrate it, but this 1 will give us an L. And we can then set this equal to 1, move over our 2 and our L, and square root both sides to get the square root 2 over L. By applying this back to our original wave function, we can get that the final wave function for a particle in a box is psi of x is equal to square root 2L sine n pi x over L.
2.
So from our first step, we found that our eigenfunction equals square root of 2 over L times sine n pi x over L. And if we plug in our n values, we'll find that our odd wave functions look like this, and our even functions look like this. Our most probable position for our odd functions are L over 2, where the peak is the highest. And for our even functions, the probability is 0 for L over 2. What an interesting fact. Another interesting fact is that these eigenvalues multiplied together and take it as an integral of 0 to L equals 0. We can prove this through this integral, and we'll walk through those steps. Here's step 1, just plugging in the eigenvalues. Step 1 to step 2, we're just going to take a trig identity. Step 2 to step 3, we're just going to take the integral of the cosine values. We'll take out a value of L over pi here. And since we know that m and n are both integers, we're going to create 2 new variables that are also integers, p and q. So we'll let m plus n equals p, m minus n equals q. So from this, we know that p and q are integer values. So if we multiply, if we take the sign of an integer value times pi, it'll equal 0. So now knowing this, we'll plug that back into our step 4 and prove that it does equal 0. So at the end of this, we will prove what we were saying earlier, that the eigenvalues multiplied together, take as an integral over 0L is 0.
3.
3, 2, 1.
We know our function can be written as eigenstates, but our total wave function will be a summation of the total eigenstates, which can be expressed by this expression here. We can then write our psi of n down into this, but in order to find our c of n, we have to multiply this by our individual eigenfunction of the wave function. And what will happen is that will get us this integral, and whenever n is not equal to m, this integral will equal 0, which means that the only thing that will be left out of it will be the c of m, or in our case, our c sub n. But what is c of n? C of n is used to find the probability of being in a specific eigenstate. Just as a wave function uses the probability of its complex conjugate multiplied by itself, we are going to do the same thing with our c of n. Some other questions you might be asking about the wave function is how does psi of x of t evolve through time? And the easy expression is that it's going to be rotating in the complex plane, and we write that by this e to the negative I e t, where this e is our energy. We can then add this to our wave function to get this expression, but we still want to find what our e is. So what is that? Remember in step 1, we found that k squared is equal to 2me over L. But we also found that k was equal to n pi over L. So we can set these equal to each other and find an expression for e sub n as n squared pi squared over 2ml. We can then plug this back into this expression up here and get our final expression of psi as it evolves through time with this.
And that's the way you do it. Particle in a box. Particle in a box, yeah. Particle in a box.
Particle in a box, baby. Electron.
Particle in a box.
Hydrogen.
Particle in a box.
Molecule.
Particle in a box.
Every type of particle in a box.
On your mod exam, particle in a box.
In your quantum nose,
Particle in a box. Doing multi-body problems.
Particle in a box. Yeah, 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 yeah.
Particle in a box. Particle in a box.